Hi everyone, welcome to Lesson 3 of our Trigonometry Part 2 unit. We are talking about reciprocals, quotients, and Pythagorean identities today. Before we get into today's lesson, let's solve this question here, our opener. This is just a quick reminder of how to use your graphing calculator from last lesson. It says here you're looking for the smallest positive solution to the equation secant x minus x equals 0, corrected to the nearest tenth of a radian. So, first things first, I'm going to need my graphing calculator in radian mode, so let's switch modes. Let's type in our equation here. We don't have a secant button, but I know that secant is the same thing as 1 over cos. Double close there, and we're going to go minus x on that as well. Y2 we want as 0 because that's our other half there. I'm in a standard window setting. This is what I get. We're looking for that first positive x-intercept there, so second trace option 5. Let's just move right on over. Hit enter 3 times once you get there. And there we have it. So on my graphing calculator, all I did was y1, y2, and I have an answer there in terms of radian of 4.9 radians. And don't forget your units of rads right on it. So today's lesson, so we have a bit of notes and then we'll get into some examples. So trigonometry identities is basically trying to solve an expression on both sides of an equation. You want to make sure that it's true on both sides. Things to take into account, you need to determine all NPVs, non-permissible values on both sides of the equation. You want to verify the possibility of identities in multiple ways. So you can use an example, aka you can sub in to verify, sub in an angle, whatever you want in. That angle on the left has to equal the same thing if you subbed it in on the right. Or you could double check it graphically using our graphing calculator, so a y1, y2 situation there. We have here what should happen when we substitute the same values in both sides of the equation for all values of x. If the equation is an identity, both sides should equal. So that's what we're looking for, is that both sides should equal. So let's quickly type that in. So both sides should equal each other. You're looking for left side equals right side. And literally this here, this little section at the end here, you're looking for left side equals right side. That's what you're looking for. So whatever your angle here on the left is, has to equal the right side there. What should happen when we graph both sides of the equation into y1 and y2 if the equation is an identity? So when you graph a y1, y2 and it happens to be an identity, your two graphs will overlap. So graphs will overlap each other. So you should only see one graph. So when this happens, you gotta watch your graphs, how they graph really quickly to see what it looks like. The other thing you could double check is you can check on your table values, and you're looking for the same values under your table values. Finally, number 3, finally, we prove identities algebraically. We'll do that later on, but for now we're mostly just working with verifying using an example and graphing. Here are some of your basic trig identities. This is all right off of your formula sheet, so you don't have to memorize these. You do need to know where to find them on your formula sheet though. So we have a few reciprocal identities here, and of course we know these already. We've been working with these. So cosecant is 1 over sine, secant 1 over cos, and cotangent is 1 over tan. Quotient identities, these we've also been working with, mostly the tangent one here. So tangent x is the same thing as sine x over cos x. That's your y over x, by the way, if it was an ordered pair. For cotangent, it's going to be the reciprocal of this, so it's going to be cos over sine. The new one that we're going to be working with is Pythagorean identities. So you know Pythagoras' theorem is a squared plus b squared equals c squared. In terms of trigonometry, what we have is cos squared x, cos squared theta plus sine squared theta equals 1. And so that's the same thing as saying a squared plus b squared equals c squared. C in this case, our hypotenuse in this case is always 1 if you want to be on the unit circle, of course. So that's why we have that designated 1 there. But that's our first equation here. Of course, I can always manipulate this equation around. I can manipulate it so that I get cos squared theta by itself or sine squared theta by itself. So be aware that we can definitely manipulate this one. We have 1 plus tan squared theta equals secant squared theta. And of course, again, I can isolate this equation for just tangent squared theta by moving that 1 away. So again, that's another identity. And the last one is cotangent squared theta plus 1 is equal to cosecant. So here we have tangent with secant, cotangent with cosecant. So again, things to kind of remember, and again, we can always manipulate around these equations. In the first example, here we go. Ooh, where are we? There we go. So it says here, verify cos squared theta plus sine squared theta equals 1 for theta equal pi over 6. Use exact values. So again, key here, exact values means whole numbers, no decimals allowed. Fractions are allowed because that's exact, and radicals are allowed if you ever need to go that way. That's also allowed. So for this one here, I'm just going to set up my equation and my sub in right away. So I have an equation of cos squared, and instead of saying theta, we're going to say pi over 6. So cos squared pi over 6. And we're going to add on sine squared, and instead of theta again, we're going to sub in that pi over 6. And we're hoping that's going to equal 1. That's our hope. So here, to evaluate this, that square don't really worry about yet. We just want to find where in cos is pi over 6, like what's that actual coordinate. If you have your unit circle available, cos of course is your x values, and you're looking for pi over 6, and so pi over 6 is right here. Cos is going to be root 3 over 2, sine 1/2. So here I'm just going to go back to this question here. So cos pi over 6 is just root 3 over 2. And now we're going to have to deal with that squared, so we're going to square that that answer, that solution there, plus sine, which is just 1/2. And we're going to square that, and we're still hoping that equals 1 there. When we square this, we get 3 numerator, 4 denominator, and we're going to add that to 1 numerator, 4 denominator. We're hoping that gets to 1. Of course, 3/4 plus 1/4 is now 4 out of 4. And of course, I can say 4 out of 4 is the same thing as saying 1 equals 1. And here, we know that we verified both sides. It does equal, so we can say left side equals the right side. And you want to finish off your proofs, because this is a verify and proof. You always want to say left side equals right side here, so that these two sides are balanced. Is cotangent x sine x the same thing equal to cos x and identity? So we want to verify using 45 degrees in this case. So let's write down our equation and sub in 45 degrees. So we have cotangent at 45, and we have sine 45 right next to it, and we're wondering if that's going to equal cos of the same angle of 45. So let's start to rewrite a few of these. Cotangent is just cos over sine. At 45, it's root 2 over 2 divided by another root 2 over 2. That's going to be multiplied, because that's my first solution there. That's going to be multiplied by, well, sine at 45 degrees is root 2 over 2 over, so root 2 over 2 there. Cos at 45 is also root 2 over 2. And really, I didn't need the brackets around this answer or the solution for cos, but I'm just going to leave it alone. Here on the left, this is just 1 because they just divide each other out. So you do have 1 times this radical root 2 over 2 is equal to this root 2 over 2. So yes, in fact, we have root 2 over 2 equals root 2 over 2. So therefore, our left side equals our right side. So we verified with 45 degrees. It does work out great. Now let's verify with pi over 3. So same thing, but instead of 45 degrees, we're going to switch over to radian mode and sub in pi over 3, aka 60 degrees. So here's cotangent of pi over 3. Sine of pi over 3. And that's equal to cos. That's equal to cos pi over 3. And again, I'm just going to go straight to my unit circle here, double checking pi over 3. Pi over 3, of course, is 60 degrees there. And so we have cos at 1/2, sine is root 3 over 2. So cos is equal to 1/2. Sine is equal to that root 3 over 2. And of course, sine is going to be multiplied by cotangent, which is sine over cos. So we have root 3 over 2, and all of that's divided by 1/2. And there we go. So we have our brackets kind of set up. Let's clean up this first one here. This one cleans up to be... Oh wait, did I have it in the wrong order? Cos over sine. Sorry, my cotangent is incorrect. It should have been the other way around. This does clean up to become 1 over root 3 multiplied by root 3 over 2. We're hoping that that's going to get us to 1/2. Here, I don't want to rationalize the denominator, because when I multiply my fractions, I'm multiplying straight through. Numerator, numerator, denominator, denominator. But here I can see that these two are going to cancel each other out. So I do end up with 1/2 equals 1/2. So there we go. Our left side, again, does equal our right side. Down here it says graph in y1, y2. Just see what happens. So let's go for it. So again, cotangent is the same thing as saying 1 divided by tangent x. That's going to be cotangent. And so we have cotangent multiplied by sine x. And all of that should equal cos x. And that's what we're ultimately looking for. Again, right now I'm in radian mode, and that's fine. It doesn't matter what mode. Again, your window setting don't really matter either. So as long as you hit graph and we have the same graph overlapping, which we do, we're good. Again, I'm going to double check by going second graph, bringing up a table of values. Our values should be very similar. We have a few errors here on the first one, and again, that's just probably because we have an NPV. For the most part, we do match up everywhere else, so we are in fact good. So graph in y1, y2, we saw the overlap. It should be the same graph there. So I'm just going to write down a quick note. Should be the same graph. There we go. In our next example, example 3, we have simplified this following expression here, right, in terms of only sine, cos, or tangent. Okay, so let's clean this up. So first things first, I see secant squared x minus 1. Well, what is that? Well, I can change secant back into 1 over cos. That's the same thing, but then I have this minus 1 to deal with. So I really don't want to do that. I don't want to switch this into 1 over cos. What I want to do is go back to my identities, a few pages back for me here, and I'm going to look at these identities here. I'm looking for anything that has a 1 in it. Well, there's a 1 here for your reciprocals, and there's a 1 down here for your Pythagorean identities. But down here most likely is what we're going to be using, because there was also an addition sign or a subtraction sign somewhere else. In this case here, we're looking for secant squared x minus 1. The only one that was secant squared theta, or secant squared x, there is right here. To get minus 1, I'm just moving that 1 over. So I can say secant squared theta minus 1 is tangent squared theta. So that's where I'm going to start. So right here, all of that there, we can rewrite that as tangent squared x. And that's still the first half here. this is going to be multiplied by cotangent squared x. So cotangent I can flip around. That's the same thing as 1 over tangent squared x. And of course, if I multiply these two together, that just tan squared x and tan squared x will just cancel out. I'm left with just 1. Okay, basically that's how we would do this one. So we converted all these into just sine, cosine, tangent. Is there definitely a second way or a third way to do this? Yes, it's however you can see it. You can definitely rewrite it that way. You could have converted both the tangents into sines and coses, and that would have worked as well. So there's multiple ways to solve this. This is just one method to do it. If you're having troubles or if you're wondering for a second or a third method, please definitely come and ask. In this example here, we have simplify 1 minus sine squared x divided by 1 minus sine x. Using once we have your answer, verify using technology ultimately. So we want y1, y2 in this case here. So what do we want to do? So we want to simplify this somehow. So here I see this numerator. I am going to double check my Pythagorean identities to see if I could do anything there. In this case here, yeah, my numerator I could rewrite in terms of this as cos squared theta, and then we can try to figure out cos squared theta equals something else. Like we can play around with it that way. The one thing I notice here though is I can probably potentially factor this numerator. The denominator here is already 1 minus sine x. There's no squares there, so you can't really factor that. But the numerator is what we would call difference of squares. And just a reminder, just a quick side note of difference of squares, it's the factoring that would look something like x squared minus 9, and that would break down into, and this is an example off to the side, break down into x minus 3 and an x plus 3. So you'd have one of each term, and everything's square rooted. That's how you do difference of squares. Here I can see something similar happening, so that's what I'm going to use. Square root of 1, of course, is just 1. Square root of sine squared x is just a minus sine x. And I have the exact same thing over here, but this time 1 plus sine squared, or sine x there. My denominator I haven't really done anything with, so I'm just going to copy it down the same. This time I'm just going to put it in brackets so that you know my denominator is all together. From here I can see that I can cancel similar terms. There we go, those cancel out to become 1. 1 times this factor is still the same factor. So you have 1 plus sine x overall. There we go. And to verify this using your graphing calculator, I'm going to type the original as y1, and y2 is going to be this 1 plus sine x. And what we're hoping to see is, again, overlapping graphs. So again, the original equation is going to look something like this. I'm going to use my fraction function just because I have that ability on my graphing calculator. So it's going to be 1 minus sine x, and notice that we can't put the squared right after sine and before x there, like how the notes have it, but our squared would work right at the end there, and that's perfectly acceptable as well. In our denominator we would have 1 minus sine x. So that's my y1. My y2, of course, we found was going to be 1 plus sine x. And again, what we're hoping is that once we graph this, these two will overlap. Again, I'm going to show you my mode setting. I'm in radian. My window setting is a standard 10 by 10. I'm going to go second graph, take a look at my table values. Yep, we definitely have some values matching up. We have an error right here, and most likely, again, why do we have an error there? That's going to be our NPV. But all the other x values, or sorry, all the other y values between our two graphs do match up, so we have overlap. And I will leave this on the screen to show you that we have overlap. So, and again, really quick notes. My y1 was this equation here, and my y2 was this equation down here. y2 was the 1 plus sine x equation or expression. Okay, that's example 4.